In the topic on malicious software, we looked at some of the software that can be used to create problems in computer systems. Viruses, worms. And sometimes we mentioned denial of service attacks. And we may have given a brief explanation to say that to do something such that our computer system is not available for the normal purposes. So if you remember back to the original topic, the first topic, I think, in the first week we listed some services that we want to provide, like confidentiality, authentication, integrity, access control, non-repudiation, and the sixth service was availability. When we want to secure a computer system, if we make that computer system available to our users, a security attack would to make that computer system unavailable. And such an attack denies the normal users use of the service. So we call it a denial of service attack, or abbreviated DoS, a DoS attack, DoS attack. So what we're going to do in this topic is look at the basic concept of how denial of service attacks are performed, to understand how they operate so that we can have techniques to try and prevent them or to minimize the chance that they can be successful, to minimize the disruption of our network or computer system. They can be quite complex attacks, so we're going to start from very simple attacks, which may no longer be used in practice today, but the same concepts are used in real denial of service attacks. And you hear about denial of service attacks in the news or in media because they are performed a lot by attackers, and they're generally easy to perform. Okay, so it doesn't take much to start a denial of service attack. So we'll see why that's the case, but there are some measures that we can use to try and minimize the chance that they'll be successful. So we'll talk about what they are, and then we'll go through some classical denial of service attacks, some very basic ones. And we'll use Linux and to demonstrate some. I'll demonstrate some in the class, and then you'll do a homework probably after the midterm where you'll do your own denial of service attack. What do we mean by a DoS attack? An action that prevents or impairs the authorized use of networks, so we can't use the network, systems, the computer system, or applications. How does it do that? By exhausting resources. So the resources that we have available run out because of the attack. So some action takes place such that my resources like CPU, my memory, the network bandwidth, or the disk runs out. So I can no longer do the normal things on my computer or my network. So a DoS attack attacks resources. So sometimes we can classify it based upon what types of resources they attack. What do they try to exhaust? It could be network resources. So if we're not looking at just a single computer but a network, then an attacker can try to overload our network. That may mean we have a link. Maybe we have a link that comes into our server, web server or some other server that we want others to access. That link has some capacity. Maybe 100 megabits per second is the capacity of that link. If the attacker tries to send traffic onto that link that starts to approach that capacity, 100 megabits per second, then the normal data coming from the normal users may be delayed or may not be sent across that link. So one aspect of exhausting the network resources is overloading the links. Sending so many packets such that the links cannot send all of them. And that often happens if the link from an organization, like your organization, your company, your university that has a service on offer, the link from the organization to their local internet service provider is often slower than the links inside the internet service provider. And we'll try and illustrate that with a diagram, but a bottleneck arises at the organizations link. For example, SIT is connected to an internet service provider to get our outside internet access. Let's say that link coming from our ISP that we pay for into SIT is 100 megabits per second. That's the capacity of our link. But within the ISP's network, they probably have a much higher capacity because they need to support multiple users. So if you think of traffic coming into SIT, then the bottleneck link may often be that one coming into SIT, the 100 megabit per second link. So if that gets overloaded, that link, that is, it's sending all the traffic from an attacker, then the traffic of our normal users will not get sent through or be delayed significantly. And if there are many packets sent in and a link gets overloaded, what happens? Eventually packets start to get dropped. My capacity is 100 megabits per second, but someone is sending at 200 megabits per second. So where do the packets go? Well, we'll show in a picture, they'll get to a router, and the router can only send out at 100 megabits per second. It's getting 200 coming in, so it must drop some. And it will drop packets, so packets from our normal users will not get to the server. So that's an example of exhausting network resources. Other denial of service attacks will look at either applications or the system. For example, try to crash the software that handles the forwarding of packets. So there's been attacks where you, say a router has software running on it that looks at the packet and then sends it on, and then looks at the next packet and sends it on. If that software doesn't work correctly, then the router may take a lot of time to look at a packet before it sends it on, slowing down all the traffic, and eventually getting packet drops. So some denial of service attacks will try to exhaust the resources of the system that is forwarding the traffic, usually using some bugs. So bugs in network protocols. Or to exhaust the applications. So for example, a web server is not just a computer, but is an application, software application running on a computer. So the Apache software is a web server, and if we can make that application slow down, then that can be considered a denial of service attack by consuming resources from that application. For example, getting the application to use a lot of RAM. Use up all the RAM on the computer such that nothing else can run on that computer. Or use up all the hard disk space. Many applications will have logs or have to have temporary use of the hard disk. If the hard disk is full, the applications may stop working. So denial of service attacks will try to either exhaust the network resources, exhaust usually the intermediate devices, the intermediate systems between the leading up to the application, and or exhaust the application itself. And we'll see some examples of that, attacks on different resources. So what we're going to do is go through two very basic denial of service attacks. The first one quite quickly, and then we'll go through the second one in a bit more depth. And I would say they're classic denial of service attacks. That is some of the most, or the original ones which are popularized. But in many networks today, they're no longer successful because there are measures to try to stop them. But they'll show the principles of denial of service attacks. And these attacks require some understanding of network protocols. And I know everyone here is experts on network protocols. Remember your knowledge of TCP? Maybe. TCP we know is a transport protocol. Okay. We know that many applications today use TCP as a transport protocol. Web browsing, email, most applications which are not multimedia applications or maybe some gaming applications will use TCP to send data because TCP provides reliability. And the way that TCP works is that before you send any data, you create a connection from client to server. So for the example of a web server, the web server is running on one computer, your web browser on another computer. Before you can send a request for a web page, what happens is that your TCP software on your web browser computer tries to set up a connection to the server using TCP. And that connection setup normally involves exchange of 3 messages. It's called a 3-way handshake. We send a special message from the initiating computer in the picture. Computer A wants to initiate a connection to computer B. So computer A sends a special message saying, let's start a connection. B, when it gets that, if everything goes fine, will send back a response saying, okay, I acknowledge that. And here is some information about me. That's what B says. And then finally A sends back a third message saying thank you for that information. From then on we can transfer data. This is called a 3-way handshake. We have three messages involved. The specific names of those messages, we refer to them, the first one as a SYN message. It's used to synchronize sequence numbers. So when we transfer data, we use sequence numbers to keep track of that data. Which number do we start at? Well, those numbers are synchronized in these first messages. So we say this is a SYN segment, saying from A, I want to synchronize with you. Here's the value I choose. B says, okay. It sent back an acknowledgement. And in addition, in that same segment, B says, I want to synchronize with you. So we say that this second message contains both a synchronized message and an ACK message, so we simply call it a SYN ACK. And the last one is A saying, thank you, I acknowledge your initial values, the final ACK. So we'll often see SYN, SYN ACK, ACK as a 3-way connection setup. After that, data is transferred. And this happens with all clients want to connect to a server. What happens when the client wants to connect to the server, in addition to exchanging these messages, the server in particular, when a client wants to set up a connection, the server will store some information about that connection. The client says, I want to start a connection with you. The server will store, when it gets that first message, it will store some information saying who the client is, the address, the IP address and port number, and maybe even allocate some memory in the upcoming data transfer, some buffer space. If it's going to use some flow control, then it's going to need some buffer space. So what B does when it receives this first SYN segment, it says, okay, we're about to transfer data with A, I'll send back an ACK, and I'll allocate some memory inside the computer for this upcoming data transfer. And that memory allocation is what leads to a denial of service attack. What an attacker will try to do is to get the server to allocate memory for many connections and eventually consume all the memory of the server, and therefore the server will not be able to accept any future connections. Let's just see the TCP 3-way handshake and then try and illustrate that memory allocation. First, and I think you have this in your handouts, this is the TCP segment. If you go forward a few pages, I've included the TCP segment. We don't need to remember it, but we do note that The segment includes a source port, identifying the application that sent the segment, destination port. For example, the source port would identify my web browser, the destination port would identify a web server, and the destination port for a web server is, everyone remembers the destination, the port of a web server. Web server 80, okay, port 80, for example, for a web server. The sequence numbers, those who passed my data communications course, who made it through to this semester, remember that flow control and error control will use sequence numbers to keep track of what's been sent. What have we received? So sequence numbers and, in addition, acknowledgement numbers are included in the header. And a number of other fields. There's data, and the flags indicate the type of message, whether it's a normal message, an ACK, a SYN message, or some other special purpose, like a FIN message or a reset message. So that's the general structure of the TCP segment. What I've set up, and I'll show you in a moment, is a simple network using VirtualBox, which looks like this. We'll use this for some demos today. We have 3 computers, 3 nodes, and you've used the nodes, I think, for homework, the past homeworks and the current Linux permissions homework. So the VirtualBox nodes, I've already set them up on my computer. There are 3 inside the same LAN for a very simple example, and node 1 has IP address 192.168.1.11. Node 2 is .12 and node 3 .13. Okay, so we can remember the IP addresses of nodes 1, 2 and 3, 11, 12 and 13. Let's just capture a TCP 3-way handshake. And in my computer, node 1 is going to be red. You'll see in a moment. Node 2 is blue, I think. That's blue. And node 3 is green, so we can keep track of the different nodes. So we have 3 nodes, and we're going to run some experiments to see what, first how TCP connection setup works, and then later some other denial of service attacks. So these are my 3 terminals. I've already started and logged into those 3 nodes. We'll zoom in a moment. So node 1, I've logged into it. It's running. It's a Linux computer. And similar node 2 and node 3. They are there. In this one, we're only going to need 2 of the nodes just to show what's going on. Node 1 and node 2. Node 2 is running a web server. Okay, it has a web server running, I hope. How do I see if a web server is running? Maybe we can try netstat. Netstat shows me the connections I'm listening to. In this case, with the -L option, it shows me something's listening on port 80. So we guess that that's a web server. There's a web server running on the blue node 2, which is waiting for people to connect to it. All right, so what I'm going to do is connect to it from node 1, and at the same time capture the packets so we can see the 3-way handshake. So I'm going to use TCP dump to capture the packets on node 2. It's recording everything it receives, and then on node 1, what web browser am I going to use? I don't have Firefox, I don't have a graphical user interface, so links, text-based web browser. Node 2 is 12. I'm just going to visit the web page. And it works. Okay, that's the default web page, and I can quit. This is the default for the web server. Quit, yes. And now I'll stop the capture. And we want to look at the packets just to see the connection setup. I could look at it on the screen, but it's very hard to see. So instead we'll try and open it in Wireshark. And here are the captured packets. And let's just focus on the TCP packets and then see what happened. So what can we observe here? We can observe that, all right, these are packets sent between node 3 and node 2. Why node 3 and node 2? Because I've got let's check the IP addresses. I've got the wrong file. Okay. I've copied this file to my computer just before the lecture, and I've got the wrong one. But I think we can still see what I want to show you at least. Here it's node 3 and node 2, whereas what I did was just between node 1 and node 2. So it's just the IP addresses are different. But it's exactly the same trace. It's one I did before. What I wanted to show you, here is a HTTP message sent by node 3 to node 2, and it's the web browser sending a message to the web server saying I want to get some web page, denoted by the /. And then the response, the web page, comes back in this message. So this is the data that's been transferred first from client to server, and then from server back to client. The web request and then the web page coming back. This was done using HTTP, but the transport protocol was TCP, and the first 3 messages, these 3, are the connection setup. And there's a lot of detail there, but the thing you should recognize, the SYN ACK, and the ACK. Client sends a SYN message to the server. That triggers the server to realize, someone wants to connect to me. And this someone is computer with IP address ending in 13 and a particular port number, 57401. So what the server does, assuming it's going to accept the connection because it's running a web server, yes, it allocates some memory, records those values, and allocates some buffer space for the upcoming data transfer, and sends back an ACK, this SYN ACK, saying thank you, let's continue, and then the final ACK. So that's the SYN ACK taking place. When we get this SYN message, memory is allocated. Let's see on our 3-way handshake. The memory is allocated. I don't want that one. This one. What a denial of service attack does is, as multiple such requests arrive, then the idea is that if many SYN packets arrive at the server within a small amount of time, memory is allocated for each one it receives, and if you have enough, then the memory will fill up on the server and there will be no more memory to be allocated for subsequent requests. So the idea is to overflow the resources on the target web server, and the way that the attacker does that is sends many SYN packets to the server. Not just one per second, but send thousands, millions per second of SYN packets to the web server. Every one that the web server receives, it must allocate a small amount of memory, but as that builds up, then the memory of the server may fill up. And if the memory of the server is full, then the next SYN packet that comes in cannot be processed because we cannot allocate more memory. Now, how does the attacker achieve this? Well, using different approaches. First, for this to work, the attacker must send lots of SYN segments to the server. And that's possible, but to enhance that, and that's what this picture shows, what the attacker will try to do is to get other computers to send those SYN segments on their behalf. And we saw in the last topic, if we have some malicious software installed on other computers, computers already infected, here they're called some slaves, the attacker has infected these other ones, and it triggers the malicious software on those computers to send the SYN segments to the target web server. So it's not the attacker's computer that's sending the SYN segments, it's other computers on behalf of the attacker. Why? Maybe they've been infected with malicious software. So that's how one way to increase the number of SYN packets that come to the web server. So you have many of these slave servers, or we referred to them as bots in the previous topic, sending packets. Then that increases the number of packets arriving at the target web server and makes it easier to overflow the memory at the target web server. Where does the SYN ACK go to? So with TCP three-way handshake, we saw when we receive a SYN, the web server sends back an ACK. Where does ACK go to? The SYN ACK message. Back to the ones who sent the SYN. Okay, so the target web server receives a SYN message. Someone wants to set up a connection. So it sends back a SYN ACK saying, okay, allocates memory. The normal behavior for TCP is we'll allocate some memory with the expectation we'll receive the ACK shortly, the third message. If we don't receive the ACK after some time, we'll deallocate that memory and no longer store it. But for a short period of time, we will allocate that memory. Now, in terms of the attacker, they don't want to receive the SYN ACK messages. There's no need to, because they're not going to respond with a third ACK. There's no need for that. It's just overloading with the SYN messages. So a common technique, again, that's used by the attacker, not just using many slave servers, but setting a fake source address when they send that first SYN message. If the source address of the SYN message is fake, where does the SYN ACK go to? It goes to that fake address, which is not the attacker's computer. And this will be a key technique which is used in other denial of service attacks. When the attacker sends a message to the server, the target, don't include your real IP address as a source, include a fake IP address. So when the server responds with this SYN ACK message, it doesn't come back to these slaves, it goes somewhere else. It's not of concern to us as the attacker in this case. So we'll see that using fake source addresses is a key part of many denial of service attacks, and we'll show that in a moment. So TCP, this is called the TCP SYN Flooding Attack. It's very simple. The attacker generates many SYN segments going to the server. It floods the server with SYN segments. Every SYN segment the server receives, it allocates a small amount of memory. And it allocates a small amount of memory and sends back a response, this SYN ACK response. But if the source address was a fake address, that SYN ACK response goes to someone else and there's never going to be a final ACK coming back. So what happens at the target web server or the target computer, it comes overloaded processing SYNs and storing connection information. Every one it receives, it allocates a little bit of memory, and if it receives millions per second, then it allocates a lot of memory, and therefore no more memory will be allowed for the subsequent SYN messages. How to stop this? It's not easy in some cases. There are some techniques which are required really an upgrade of the TCP software, so they wouldn't handle that. And that upgrade is sometimes implemented as SYN cookies. So there's an extra check to make sure that this is really a true connection request from a client. Another way is to filter packets. If we receive millions of SYN packets from a particular source, then don't let them in. But we'll see that there are problems with filtering packets. So TCP SYN flooding was one of the earlier, or one of the main denial of service attacks in the early days. It's not so common today because of the filtering and because of some of the countermeasures like SYN cookies which are used. There are limits on the number of SYN messages received. So this is an example of overloading the application. It's not overloading the network. They're only small packets. It doesn't use many resources. It's overloading the application on the target computer there, using up the RAM usually, or the CPU. Let's look at a similar type of attack, but it's overloading a different resource, and it's called a ping flooding attack. Flooding means to fill something up, in this case for a network, to send many packets. We'll go through and look at a similar type of attack called a ping flooding. Before we go through, another reminder, the IP address format. The IP header format, sorry. So this at the bottom is the TCP header format, and also as reference, this is the IP header structure. What are the two most important fields in the IP header? What would you say if that was an exam question, or if we have a quiz next Tuesday? The two most important fields in the IP header. From our course perspective, or from what you know, source and destination are two things that we always come across. Who's sending it? Who's receiving it? Right? There are many fields here, but from our perspective, we often care about who's the source and who's the destination. Right? There are some other things about the length and the type, but that's important. From a security perspective, first it identifies computers. The source address is, in theory, it's the address of the original sending computer, and the destination is the final destination. So when I send a packet from my laptop to the Facebook web server, the source address of that packet would be that identifies my computer, and the destination address inside that IP header will be that identifies the Facebook web server. So IP addresses act as some identifier of the computers, and that is some security issue in terms of privacy. If someone can observe this header, they can see who's communicating. Now there are some special cases or some other issues that arrive that make that not so easy to identify individual computers, but generally we assume that computers can be identified by the IP address. From an attacker's perspective, that's bad, because one of the ways to stop attackers is to identify who they are and maybe send the police around to them and tell them to stop, okay? But to take actions outside of the computer system. So what an attacker would like to do is to hide its IP address. And one way, quite simply, is to send a fake IP address when you send packets. Set a fake source address. So we'll show how to send set fake source addresses as part of attacks. But setting a fake source address also has other benefits. So let's go through a ping flooding attack. Before we explain this network setup, let's demonstrate ping. We'll zoom in a moment. What does ping do? Ping, very simply, as an application, triggers, when I run the application, it triggers my computer to send a special message to the destination. In this case, from my computer, node 1, to 192.168.1.12. In this case, repeat 5 times. And the protocol being used, it's not TCP or UDP, it's a special one called ICMP, the Internet Control Message Protocol. And the way that it works is my computer sends a ping request to the server, to the destination, not the server. The destination computer, when it receives the request, in the normal case, sends back a reply. And when I get a reply, my ping software prints a line on the screen saying some information about that reply. It took 2.85 milliseconds to get there and back. And then in this case, it does it again. It repeats 5 times. So ping involves sending a request to the destination and getting a response back. Sometimes we say an echo request and an echo reply. How big are those messages? Approximately. How big are the packets being sent across the network in this case? Megabytes? Gigabytes? Approximately, how many bytes? Can anyone see the number up there? 64 bytes, all right. There may be some header and some other overheads, but we're talking about 100 bytes or so. Because it says here, there was a reply that we got 64 bytes from computer 12. When I pinged from computer 11, the red one, to computer 12, 64 bytes come back. But we know that there may be some overhead due to headers, like the IP header, maybe another 20 bytes, the Ethernet header and so on. So we're talking about messages in the order of 100 bytes. Not very big, quite small. Can we make them bigger? How do we make them bigger? Yeah, we can make them bigger, as big as we like, although there may be some limits. We can set the size. Okay, so we've got bigger packets. So ping is very simple, and ping is supported by most computers. They will respond to ping. Okay. Now, let's see how ping can be used in a denial of service attack. Here's our example network structure. We say there's the attacker, maybe the attacker's computer. They have their local network, maybe a LAN, and this is a router. Say the attacker owns a router at home or in their business. And the attacker gets access to the internet via an internet service provider. Tell me 3 internet service providers you know of. Anyone? Who's an ISP in Thailand? True. AIS, DTAC, you're talking about mobile phone providers. Yes, they are internet providers also, but yeah, there are a number of ISPs. If you look on maps of the internet, there are tens of, or even 100 plus companies that provide internet service inside Thailand. So what we do as an end user, we pay the ISP for access, and we can think of the network structure is that for if I'm the attacker, my router has a connection going into the ISP's network. Right? There's a cable coming into my home from the ISP's network or into my business, and the internet service provider has some router, then they connect to a larger ISP. Maybe a small one connects to a larger one, and they connect out to other ISPs in other countries, and that's what the internet is made up of. Now think of the target, maybe some organization, and the target maybe say a server in that organization, maybe a web server. The attacker wants to make it so that others cannot access this web server. So we can think of the target computer, and the similar structure. The target has a network, their own router, and they connect to the internet via their ISP, right? The internet service provider of the target, and they connect out. Now, let's assume that in terms of the links between the attacker and the target, let's assume the slowest link across that path is this one leading into the target's network. Let's say that's what we call the bottleneck link, the slowest one. Maybe internal for the target's network, they've got a fast LAN, very fast there, but when they pay for a connection to their ISP, that's the most expensive part, and therefore that's the slowest part of the network. Across the different ISP networks, usually they have very high speed links. So across True's network, across TOT's network, inside their network, they have very high speed links, but going to the end customer, that's one of the slower links. So let's assume that's the bottleneck link. And that the attacker, they also connect to an ISP, but it's faster than the targets. That may not be so realistic, but we'll come back to that in a moment. So this is the bottleneck link. So what the attacker tries to do is to send enough packets to the target such that this bottleneck link is overloaded. It has some capacity. If we send enough packets in such that we start to reach that capacity, then the link is carrying packets from the attacker, and it cannot carry the packets from the normal users. And normal users out on the internet that are trying to access the target web server cannot access. They're denied service. That's the idea here. How that is achieved is by the attacker sending enough packets such that the input to this router approaches the capacity of the link. If we want to put some numbers to that, let's say, just for this initial case, that this link supports, say, 100 megabits per second. I will not write the units, but in terms of capacity, everything in megabits per second. Maybe this one supports 2 megabits per second. This one's 100. This one's 10. And every link inside here is much faster than the others. So by the bottleneck, this is the smallest in the path. So for a denial of service attack on the network resources in this case, what we need is that the attacker sends packets at a rate such that coming in here exceeds 2 megabits per second. That's the idea or the aim here, or gets close to in most cases. That is, the attacker wants to send enough packets such that coming into this router is greater than 2 megabits per second, because the output is only 2 megabits per second. And what happens then is that as packets come in, only 2 can come out, the others are dropped. So if there's 3 megabits per second coming in and only 2 going out, then 1 megabit per second is going to be dropped. And that will include packets from the normal users, those that want to access the web server. So the normal users are out on the internet, and they're trying to access the target web server as well. Say it's a website, they try to visit the website. When they send their packet to connect to that website, the packet gets to this router, and there's a high chance it will be dropped or at least delayed a long time, because this router is handling the many megabits per second coming in from the attacker. So that's the idea, that the normal users will have their packets dropped. They won't be able to connect to the target server. So this is an attack on the network resources, in particular on this link. The question is, how do we generate so much traffic? What's your idea? How do we generate, as the attacker, so much traffic so that we overload this link? Multiple ways, maybe multiple different sources. What application, what software could you use to attack? You get all your friends to open their web browser and type in the URL and click on the link and press refresh many times. Okay? You've got 100 friends and you tell them, let's all at 6 p.m. today refresh on this website so it sends many packets. Well, the dimensions of these links are not in the order of 2 megabits per second. They're usually much, much larger, such that manually it's very hard to overload like that. Okay, you need maybe hundreds of thousands of people to be doing that. So it's very hard to manually do that. What we need is some automatic way to do that.
Actually, didn't this occur last year?
I think it wasn't last year, this year, or yes, there was talk, or late last year there was talk that people were doing that to try to bring down websites. But generally it's not a very effective denial of service attack because it requires many people. Right? It's very hard.
The thing is that the event that occurred was quite effective.
Right. It depends upon the capacity here. Right? But for, let's say, very popular websites, they'll have a lot of capacity here. It wouldn't be 2 megabits per second. It may be hundreds of megabits per second, gigabits per second, and in fact the website may be distributed across many different servers. So you need a large amount of traffic to slow it down. And for that you need to automate the sending of packets, and the simple approach we'll look at is using ping. Because with ping, the nice thing about ping is that most computers respond to ping or let it through. With ping we can set the sending rate. We can change the interval. So with ping we can both set the size of the message and set the rate at which the source will send. So here's 2 times per second. Can we set the rate lower? 10 times per second. It says no, but if we have administrator rights, and we do as the attacker, it's our computer, we can now send 10 times per second. And in fact, in general, we can send as fast as our computer will handle. So what the attacker will try to do is send these ping messages as fast as possible, such that all of those add up and overload the bottleneck link into the target's network. So that's the concept of the simple ping flooding attack. The target bottleneck link receives many of these echo request packets from the attacker such that the link is overflowed. The ones that do get through, the target receives the echo request, and with ping you send back an echo reply. You send back the response. So all the replies come back to the attacker. So that's the simple attack. You're the attacker, what's wrong? What do you not like about this when you do this attack? He knows everything. I'm looking for someone, I'll ask him in a moment. He doesn't have to sit the exam, you do. He's just here for fun. Yeah. Mark's here for fun. Anyone else? What's wrong from the attacker's perspective? All right, we can't wait too long. Mark, what's wrong?
The target knows the IP of the attacker.
The target knows the IP address of the attacker. Okay, here's one problem. Here I am, the attacker. I'm sending the message to the target. Inside the IP header is the source IP address. So the target, yes, it's being attacked, but it knows who's doing it. And now they call up the police and send them around to or they call up my internet service provider, more likely, and say, you've got a customer that's doing a denial of service attack on me. Please stop them. Okay, so there's the first problem here. Because the IP header, and IP is the protocol being used to carry ICMP, the IP header contains the source and destination address. The target knows the source, which is the attacker. So the attacker is identified. So that's a bad thing from the attacker's perspective. Yeah. What if the attacker uses some VPN to change their IP address? So a VPN would involve, and we'll cover it in another topic in detail, but basically the attacker sends to or gets another computer sent on their behalf. All right? Then what does the target identify? It identifies the VPN server. Okay. Now, can it then trace it back to you? It depends on whether you're paying for that VPN account. The target comes to your VPN provider and says, at this point in time, someone was doing a denial of service attack. The VPN provider looks up their logs and say, that's this customer. I'll stop them from using my service. Okay, so it's not hard to trace back if they take the right means. But we'll see that it can be hidden to some extent. So that's one problem. The IP address identifies the target, identifies the attacker to the target. What's another problem from the attacker? Even if we didn't worry about being identified, I'm getting all the responses back. That's a bit of a problem. My network slows down too, right? Let's say I need to send at 100 megabits per second and I'm getting all the responses back at 100 megabits per second. So that can be inconvenient for the attacker. So the idea, flood the server. The attacker uses ping to send many ICMP requests to the target server. It overloads the link to the router of the target network, and that starts to drop the valid packets, the packets of the normal users trying to access that website. How do we stop that? What are the countermeasures we have available? We could get the internet service providers to block ping packets. Don't let them to be sent through our network. Well, that's a possibility, and some organisations may do that, but it's a bit of a problem because ping packets have a legitimate usage. They use for testing connectivity, for measuring delay. So if everyone blocks them and don't let them be sent, then we lose some functionality. And not many ISPs will block ping packets. Some do, and you may find that SIT blocks ping packets going out. So that's one way, but it has a drawback that now our normal application is no longer supported. The other thing, like we saw, identify who started the attack. Identify the source based upon the IP address and take some action. Contact their ISP. You can identify them from the IP address and say, this person is doing an attack on me, stop them, or we'll take you to court, or you take the customer to court or take legal action. So that's another response. And the other problem is that the attacker's network is overflowed with all the responses. So that's something we'd like to get around from the attacker's perspective. We'll see that in a moment. So, what we want to do from the attacker's perspective, the other problem is this assumption. The attacker has access to a high capacity link. Let's say I want to attack a website, and I found out that website has a 1 gigabit per second link coming into it. Therefore, I need to pay for a link which is at least 1 gigabit per second. How much is a 1 gigabit per second link into your home? Okay, you probably can't buy one in many places, all right? So we assume that the attacker has access to a high capacity link. So there's maybe a high cost involved from the attacker's perspective to do that. Because the web server is usually run by an organization and they have a lot of resources. The attacker may not have so many. So how can we get around that from the attacker's perspective? And the approach is to use multiple computers to do the attack. So we'll go through the different things that the attacker can do to try and improve the success rate for the attack. The first thing, I don't want to be identified. I don't want the target to know who did it. Use a fake source address. It's called source address spoofing. We have a fake or a spoofed source address. And it's quite easy to do. So this just repeats the IP packet header. We assume that every packet sent, the source address is of the sending computer, the destination is the target. Therefore, the target can identify the attacker. That's the problem. But it doesn't have to be the the attacker's address in the header. The attacker can change this address because it's their computer that creates this packet. They can set it to anything that they like. That's how they set a fake source address. As a result, the target won't know who performed the attack, at least without some further investigation. The other benefit from the attacker, the responses are not sent back to the attacker. The responses are sent to the fake address. Let's see. We'll show you how to set a fake source address and see it take place when we use a ping. We'll just ping and see what happens when we ping computer 12. We can quickly see what happened here. When I ping computer 12, the ping packet we call an ICMP echo request. Zoom in. One more. Here we sent from computer 11 to computer 12 an ICMP echo request. Computer 12 with the next line sends back a reply. So this is just ping working. 12 sends back a reply to computer 11, and then in this case I did it 2 times. I had a count of 2. So that's ping working. Let's try with a fake address. The red node I want to set as my attacker, and I'll first set a fake address. And there are different ways to set a fake source address. In Linux, one simple way is to use the firewall software called IP tables. You don't need to remember this command at the moment. We're going to do a process called network address translation. I'm going to translate my real address into a fake address. Do some translation. What I'm going to do is, after I send the packet, or after I create it, to change the address. So I'll add a rule, or a rule that will change the address. I missed a letter. Using ICMP, whenever you use ICMP, use a fake address. And we're not trying to explain all of it. Do some what we call source network address translation. As the attacker, I want to change my source address from my real one to a fake one. I'm going to translate my source address. And I want to translate it to I choose a fake address. There's a mistake there. Okay, so this is the command I'm going to use, and I'm on node 1, the attacker's computer. And the idea is, when I run this command, every ping packet I send, the source address will not be my computer address of .11, but it will be .66. We will capture on computer 2. We'll zoom in a moment. Now I'm going to ping computer 2. Do I get a reply? No. So what's happening is that when I run ping here, and I can stop it because nothing's, or it stops by itself. When I run ping, my computer, we'll see in the trace, sends out an echo request, but the source address is .66. The packet gets to computer 12. How do I know that? It'd be hard for you to see, but it's this line says, computer with IP address 12 did receive an ICMP echo request. It received the request, and that request came from computer 66. So 12 received the request from computer 66, and with ping, what do you do when you receive a request? You send back a reply. Who do you send the reply to? 66. So what my computer does, this is node 2 does, it wants to send to 66, but on a LAN you need to know the hardware address of computer 66, and the way to do that, you use a protocol called ARP, Address Resolution Protocol, saying who has the IP address 192.168.1.66? If you do, tell me. And it's sending out a message to everyone, who is number 66? And it's not going to get a reply because there is no 66 in the network. It gets no reply, and hence it will never send the echo reply back to anyone because it doesn't know who 66 is. So what's happened here, when I set a fake source address to be someone who doesn't exist, the target still received the packets but didn't send a reply back to me as the attacker. And that's a good thing from the attacker's perspective. The target still got the echo requests, but it didn't send back the replies. So the attacker doesn't get the replies, which is good. And who did the attack? From the target's perspective, computer 66, not the real attacker. Yep.
What about if we change the source to the destinations?
What if we change the source to the destination? then I think the destination would identify that as an error. Okay, if I receive a message and and the source is the same, then it would detect that that's something not to respond to. We will not try it. We'll try another one in a moment. But there is another way to handle that. So here's a fake source address. Very easy to implement. You can do it on any computer. What fake source address should we use? Here I used it, I chose a random one, 66. Another thing we'll see later, what if I choose someone else's address as the fake one? What if I choose computer 3 as the source? So in this case, what's happened in that very, very simple case was my source, my attacker, sent a packet the echo request is sent to computer, I've gone the wrong direction. It's sent to computer 2 in my case. But the source address was set to the special 66, or the 66 address, the fake address. The destination was 12 in the IP header. This one receives the echo request and then it tries to find someone to reply to. It couldn't find anyone using ARP. Another case we could do is set the source address to be computer 3's IP address. If it was source address of computer 13, then it would reply to that computer. And we'll see that's another feature that can be used in a denial of service attack. It's called reflection. We can bounce the message across another computer. So what we could do from the attacker's perspective, let's say we want to attack computer 2. We could send to computer 3 first and then get them to send to computer 2. Source equals 12, destination equals 13. Computer 3 receives it. Where does it send the reply to? The source of 12. So that's the next way that we'll use the fake source address. Get another computer to send to the target on our behalf. So in this case, I still want to attack computer 2, but I send the message to computer 3 first and set the fake source address to be that of computer 2. So when computer 3 replies, it goes to computer 2. So that's the use of the fake source address, not just hiding who the source is, but also getting another computer involved to do the attacking. So let's see that on our attack. The idea is that our attacker now, whenever it sends a ping packet, it sets a fake source address. And it changes that source address on a regular basis. So what happens, we send the ping packets to the target gets them and replies to some fake or some other computer. The benefit, the attacker doesn't get the response messages. Another benefit, the target can't identify the attacker. They see it as someone else. So that's the use of the source address, fake source addresses. And the other approach is called reflection, which is you set the destination to be one of the other computers and the source address to a fake address, which is that of the target. So the approach is, I want to send to the target, but what I do is I send the ping messages to these other selected, maybe randomly selected computers, ping them, but with a fake source address, where the source address is that of the target. So this computer receives an echo request, source is the target, therefore I should send the reply to the target. All the other computers receive echo requests, and they all have as the source address in those requests the target's IP address, so they all send to the target. So we bounce the messages off the normal computers. And this can have the benefit because now the target is not receiving messages from all of the one address, it's receiving from many others, and it can be used to bypass some filtering techniques that some organizations will use. So the source address is a very powerful technique to support denial of service attacks. We can reflect the attack. But the details I think we'll return to in the next lecture. We'll go through and look at what are the countermeasures for using fake source addresses, and then how can we expand upon this attack to greatly increase the number of packets being sent. So we'll talk about the capacity and how to overload the server. So we'll do that next Tuesday.